Okay, I think everybody is here. So now this time we continue our discussion about Hamiltonian constraint. Just a moment. All right, about Hamiltonian constraint. So I think it is good to just review some history. So I talked a little bit about history about Hamiltonian constraint last time, but I think I better talk some little bit more detail about history because Hamiltonian constraint it's really play the central role in the development of quantum gravity. so firstly, let's say before um, 1988 or 87 or 80 or 88, let's say. So there were that time quantum gravity was only developed in terms of ADM variable. So quantum gravity with ADM formalism, right? And since we learned what is ADM formalism, we know that canonical variable are just are PAB and QAB. These are canonical variables, and then okay, naively you can formally consider your wave function just a function of Q, right? And then your P operator, your P AB will become operator PAB. Operator PAB is going to be just the derivative operator. Okay, derivative operator, just like quantum mechanics. And now you just get an infinite number of degree of freedom. So it's just a minus I h bar delta QAB x. So which means now since you have it's a field theory, you have infinite number of degree of freedom. So your derivative operator is not ordinary partial derivative, but a functional derivative. So you have to use delta QAB. It is well, it is formal, but well, you can write things like that. And then your Hamiltonian constraint reveal that in ADM formalism, your Hamiltonian constraint is 1 over kappa square root determinant Q, and you have PAB minus 1/2 P squared. So here basically you get firstly you can view it is like a kinetic term which is quadratic in P. P is your momentum. So you get a kinetic term which is momentum squared somehow. And then you get another thing like a potential term. Yeah, but this potential is just a free curvature which is function of Q only. Okay, so now what you are going to do is define a C hat, right? A C hat. The how to get a C hat is just replace every quantity in the formula by the operator counterpart, and just well Q just the Q hat, right? And C hat is just a C with Q replaced by Q hat, Q of X, and PAB and PAB X replaced to be this derivative operator. QABX. Okay, so this is your quantum Hamiltonian constraint in ADM form in old quantum gravity formulation, and then formally you want to solve this equation well as a function of Q, functional of Q. So these are because Q has infinite number of degree of freedom, so it is functional of Q. Okay. Okay. you just want to solve this equation. Okay, and this equation, it is a functional differential equation. Functional differential equation. It is complicated, very complicated, because you involve infinite number of degree of freedom. So you see that if you solve a partial differential equation, it's going to be more complicated than ordinary differential equation, because you have multi-degree of freedom. But now you have infinite number of degree of freedom, so you have really a functional partial differential equation. Yeah. So this equation, it has a name because it was the first equation about quantum gravity. So this is called Wheeler-DeWitt equation. Wheeler-DeWitt equation. Okay. So, okay. So in old times, people try to solve this equation, but of course it is extremely difficult. It's even hard to make it well defined. It is very hard to make it defined. So of course you are not able to solve this equation in general. Okay. And so that's why at that time quantum gravity becomes stuck. And now when, let's say, starting from 1988 to 1996, let's say. So now we have Ashtar variable. So Ashtar comes and design the Ashtar variable. And you have the canonical variable is EAI and AI. Okay. And now we have holonomy and flux and all those quantization procedure I just discussed. And you have the Hilbert space, and your wave function is function holonomy. Wave function is a function of holonomies. Okay. Okay. So everything. So at least from kinematical level, about Hilbert space and wave functions, it's become very well defined, and your operator, your holonomy is just multiplication operator, and your so E become a flux operator. Yeah, it's become right invariant vector field, and all those operators become well defined. Okay, so then immediate task is to look at the Hamiltonian constraint, and we know from earlier discussion that our Hamiltonian constraint has a Euclidean term and a Hamiltonian term. So let's just look at the Euclidean term. So 1 over kappa. So yeah. So the Euclidean term usually is called FEE because it's written as FEE. Okay, and there's a square root Q and plus the Lorentzian term. Lorentzian term has extrinsic curvature. It's going to be more complicated than the Euclidean term. But then the first idea is still similar to Wheeler-DeWitt idea. So you just replace E and how to quantize this C, these Hamiltonian constraint. You just replace EAJ to be X to be just the functional differential functional derivatives. H bar. Well, so this is probably H bar kappa. Well, according to you have to respect to the commutation relation. So here, I guess it should be LP squared divided by beta LP squared divided by half, I think, and then delta A X. Okay. And now you promote your C to be a operator, C hat. Okay, but unfortunately, and this operator is still not very well defined because you still use functional derivatives, and also you don't know how to deal with this square root Q. in the denominator. Yeah, and you have the same problem I mentioned before. So you have to somehow relate this, how to quantize this, how to get 1 over square root determinant Q quantized. Yeah. So this is the question, and you have to quantize it so that it has no divergence. Yeah. How to get these without divergence. Okay. Yeah. So it was a problem that time, and then so in 1996, 1997, and then Thomas Tiemann comes. So even Tiemann's Hamiltonian constraint. Tiemann's Hamiltonian constraint. Okay, so I mean, it is really an advance that Tiemann can really rigorously define these Hamiltonian constraints, and at the quantum level, yeah, he can really quantize these constraints as an operator and make everything well defined and defined on the Hilbert space. And it has been done in the history of quantum gravity. So this is, you can see this is really a milestone of quantum gravity. So starting from Wheeler DeWitt, people completely has no idea about how this operator looks like, but now we are able to write down this operator. Okay, so now let's come to the construction. So the one of the idea, so as I mentioned last time, is this Tiemann's trick. So I write it again. So we have this lemma. So the Poisson bracket. So basically to how to regularize, how to re-express this EE divided by square root of Q. Okay. So right. Okay. So before, is there any question? So last time I have written the Euclidean Hamiltonian constraint, the Euclidean term in this expression. So this is -2, and we have trace AB, EA, EB commutator divided by determinant Q. So by the way, last time there was some question about this commutator. The commutator here, it is not a quantum commutator. This is not the quantum commutator of operators. These are just the commutator of SU2 Lie algebra. So this is the commutator of SU2. Yeah, namely, it is just the commutator of 2x2 matrices because EA is EA J tau J divided by 2. Yeah, tau J is I times a Pauli matrix. Tau is minus I times a Pauli matrix. Okay, and here this trace is also taking just the trace of 2x2 matrices. Okay, so don't be confused with operator commutator. Okay, so now our lemma is that you can express this quantity in terms of Poisson bracket between connection and volume. A region. So if you have a point X and you have a region such that X belongs to R, and if you compute the Poisson bracket between A and V, you just get these quantities. There are some prefactors minus kappa beta divided by 8, and there is a sign of determinant E. So this formula relates to either you use a right hand frame or left hand frame. Because here it relates to E, so it depends on E is right hand or left hand. E and is epsilon ABC. Okay, so here you got these because EAJ equals to square root determinant Q EAJ. Okay, so here this means that EAJ right hand, right or left, then this sign determinant E equals to plus or minus 1. Okay, so or this is just a sign of really just what is written. If you compute determinant of E, and this is just sign of the determinant. Okay, so this is what we usually call Tiemann's trick. All right, so let me prove it. Prove this lemma. This is just a simple calculation. Okay. All right. So now let's look at the volume. So remember we have discussed about volume. So this is classically just integrating over a region R, three-dimensional integral, and determinant of Q. Okay, and now you can. All right, so suppose you take the, so here you only need to compute the Poisson bracket between volume and the connection, so which reduced to just the functional derivative of the volume with respect to E, with respect to density type prime. So what you only need to compute is, because E and A, they are conjugate. I, okay, so these we just apply it to this integral. Okay, you just have a functional derivative act on determinant Q, but then you can compute the derivative. So what you get is 1/2 determinant Q, and then functional derivative act on determinant Q itself. I better put a prime for the dummy index. Okay. So yeah, so this functional derivative is located at x. So the integral, I put x prime. Okay, and we know that determinant Q, it is, so this determinant Q, it is just the determinant E, determinant EAI, but you have to put an absolute value because determinant Q is always positive, but determinant E can be negative, and can be negative if you have a left hand frame, right? So they are equal if you put a sign, yeah? If you put an absolute value, yeah. And then determinant. So here the determinant E is 1/6 epsilon ABE epsilon JKL EAJ EBK ECL. Okay. So now you can express this determinant Q in terms of E, but the only price to pay is you have to put absolute value, and that's the origin of this sign of determinant E. Right? So this is, you can write, this is just you can replace this absolute value to be just determinant E, and multiply sign determinant E. get just absolute value. Okay, so now, well, this is just the overall. This is just a constant sign. It's depend on your choice of left-hand frame or right-hand frame. So it doesn't participate in the derivative. Okay, and you can just let your derivative act on this determinant E and do the calculation. Okay, so now we can proceed. X prime are okay, and you pull out the sign factor. E. And now you you let your derivative act on those E's, act on those three E's. You got three terms, but you got actually three identical terms because, well, JKL, ABC, they are a contract with epsilon. So you will derivative, you will have three terms if you use the product rule of derivatives, but all those three terms will be the same, and so it cancels 1/6. You got 1/2 epsilon ABC epsilon ABD JKL and delta J X prime E C prime X. Okay. So this is the result you have. All right, so now, I mean, you are just making this functional derivative of E with respect to E, and what you get is just delta functions. You get delta A C, delta I J, and delta 3 X prime and X. Okay. And now you can, because you have a delta function, you can just integrate out this integral. So I mean, integrating out the delta function, you just replace all x prime to be just x, or square root determinant q psi e, and okay, epsilon ABD. Now, so here you have to replace A by C, J by I. E, K, C. Yeah, so this is the result of the functional derivative of volume. Now you are going to use this formula. So let's just compute the Poisson bracket between A, C, X, and volume. Okay. So firstly, this A, C, X is a matrix. So it's the tau J divided by 2 A, C, J, X, volume. And this equals to J. And you just use product rule for the linearity of the Poisson bracket. So A, C, J, X, E, A, J, X prime. And delta V of R, delta E, A, J, X prime. Okay. And then these three X prime. So this is not a linearity of the Poisson bracket. This is probably called the chain rule of the Poisson bracket. Okay, so now you get a Poisson, just this is just Poisson bracket between canonical pair, and this, according to our convention, this is minus kappa beta divided by 2 delta. So this is better. So sorry, in my note I use I here, I, and this is I, this is J. Right? So this is delta ij, delta ac, delta 3 x prime. Okay, and you get the deltas, and again you integrate out x prime. Okay. So these you get 1 kappa beta minus 1 minus kappa beta divided by 2, and then tau half, tau I, and then delta v r delta, and so eci x, and this is exactly what we are just compute. This functional derivative equals to this. Okay, we just apply this result. This equals minus kappa 2 I up psi e 1 over okay 1 over 4 I put this together with 4 and epsilon c bd epsilon I k okay cl. Okay, now I can use commutator to replace these parts, and also and together with this this matrix. Okay. So this beta sine, okay, and 1 over 4 CBD, and determinant Q, and commutator E, EC. Okay, so yeah, this is the result. This is exactly the result of the lemma. Okay, so this finished our proof. All right. So well, to better use this formula, sometimes it is very useful to just to make a multiplication to contract this formula with another epsilon. So to move this epsilon to the left hand side. Okay. So so you can write equivalently commutator EB EA EB determinant Q equals to minus 4 theta, closing bracket AC B R DC sine determinant B. Okay, because this guy is the building block for the in the Hamiltonian constraint. Okay, so but you can see that, well, let me write again the Hamiltonian constraint. Euclidean Hamiltonian constraint is you see the prefactor minus 2 divided by kappa, minus 2 divided by kappa with Q EA. Okay, so this is your Hamiltonian constraint, and then what we are going to do is just going to plug in this formula, okay, to replace this gadget. But then you can see that there is something problematic because you have a sign, yeah, and well, and so when we come to the quantization, we wonder how we quantize this sign, because this sign doesn't really, well, this is just a sign. It's not continuous. It's not a smooth function in the phase. It's dependent on the E, of course, but this is not a smooth function depending on the E. It's jumping. So determine the E from negative. Determine E is negative. It is negative. Determine E is positive. It's positive. It is not continuous. So what we actually so therefore, to solve this problem, what we are actually quantizing is not really these. It's not really this Hamiltonian, this guy. But what we actually quantize is psi determinant E C0. Yeah. So this equals to, right? This equals to -2 divided by kappa trace FAB and psi determinant E and Q E commutator. So what we are actually quantizing is not naively the Hamiltonian, the Hamiltonian constraint, but instead we multiply a sign factor in front, and this is the quantity we are quantizing. Okay, so this is what we actually quantize.